Alright, hello everybody, this is Dr. Pennington again. I want to do right now a video which is kind of an extension of the Lewis structures video that you just hopefully saw. And on that last video I did reference the formal charge, but we didn't really use it all that much. I told you that formal charge is used to really determine how stable or happy an atom is when it has a formal charge of 0. The higher above 1 or lower below 1 the formal charge is, the less happy the atom is, the less likely it's going to form in that way. And why is my pen moving? Well, I think my software is possessed. Maybe Charlie Sheen has got on here. Anyway, what do you do when it appears that you have two or more Lewis structures, both or all of which appear to be identical? Which one of those is correct? Now, what do we mean by that? What we mean is, I'll just arbitrarily draw on the board. Now, what we really mean is, for example, the carbonate ion, CO3 2-. Alright? First of all, let's figure out the number of valence electrons that we have to place here. Well, carbon has 4 electrons, oxygen has 6, and there's 3 of them. Now that's 18 plus 4 is 22. That would suggest 22 valence electrons. But there's one other thing here. So Lewis structures of neutral molecules is not exactly the same as Lewis structures of ions. We have to take into account the 2- somehow. 2- implies 2 extra negative charges, hence 2 extra electrons. So the way we figure that out, or we factor it in, is add 2 electrons to the total. Okay. Now, look at the carbons here. And actually, before we say that, before we go any further, the fact we have 2- here tells us we have some formal charges of something other than 0 in our molecule. It means that we're going to have one or more atoms with not the normal number of bonds. Okay? It means they're slightly less happy, but they don't really have a choice based on what we're going to see. And 2- usually means 2 atoms, each of which have a formal charge of -1. The likelihood of seeing a 2- charge on one atom is very unlikely, so it probably means 2 1- charges. Alright, let's go through our rules that we did before. What's our central atom here, most likely? Well, it was carbon before, and it's carbon again. So, carbon. And we can see there are 3 oxygens around it, so I'm just going to draw them in kind of a triangle shape. That's a common sense thing to do. And then I'm going to do what we did before and link them up. But we need an octet of electrons around each atom. And if I say, well, I'm going to complete the octets of the 3 oxygens by doing this, I want to see if you guys can figure out what the problem is. Well, the problem is, first of all, none of the oxygens have the required number of bonds, or have the usual number of bonds. Oxygen usually likes 2. But more importantly, and more of a problem, is that the carbon does not have its octet fulfilled. You remember, that's the thing that you absolutely cannot break unless you're under special circumstances. Each atom has to have its octet filled. So that means bollocks. Bollocks, bollocks, big hairy bollocks. It means we have to redo this. We're going to redraw the oxygens on. That's fine. But I have to find a way to give my carbon 8 electrons. The most common way that we saw before was to give it 4 bonds. And can you see that I have the option of giving it 4 bonds here? I can just draw a double bond to any of my oxygens. And herein lies the issue. Does it go here? Or does it go here? Or does it go here? What I want to do at this point is draw out 3 separate structures where I do exactly that, where I put the oxygen, the double bond to oxygen, in the 3 different places, like so. Now, at first glance, it looks like these are all exactly the same thing. And it's a completely understandable point that you would see it that way. But the thing that I want to do is to give each of these oxygens a little subscript number, just so you can see that each oxygen is being considered differently. Alright? It doesn't mean 3 oxygens or 2 oxygens, it just means oxygen number 1, 2, and 3. Now, before we go any further, we're going to complete our octets and have everything done. Carbon is happy, it's got 8 electrons around it. So let's look at this oxygen here. It's got 4 electrons around it, so it needs 2 more sets of lone pairs. This oxygen is in exactly the same position as this one, so we're going to put those electrons around here, and then this one's exactly the same too. Now when we come to this oxygen has 1 bond to it, 2 electrons around it, so it needs 6 more, or 3 lone pairs. And notice, because that one's singly bonded, so is this one, it should be in exactly the same situation. And no coincidence that it actually is in exactly the same situation. In fact, we can say that across all of these. So what we're doing in each case is adding 3 lone pairs, 6 electrons around each oxygen. Now, we need to stop and just think about this for a minute. We have our formal charges here somewhere, and now is a good point to factor in where those actually are. Formal charge of carbon here. Well, carbon has 4 valence electrons minus 4 bonds plus 0 lone pairs. So each of the carbons here is happy, 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 happy. Look at the oxygen that's got 2 bonds to it. I guess I shouldn't have drawn green. Oh, right, never mind. Each oxygen there has, or the oxygen here has 2 bonds and 4 lone pair electrons. The formal charge on that oxygen is 6 for the valence electrons minus 2 for the bonds to the atom plus 4 for the lone pair electrons, given a formal charge of 0. Which means here it's 0, here it's 0, here it's 0, which means the formal charge of 2 minus must be coming from these 2 oxygens, from these 2, and from these 2. Remember, I'd said previously that when an atom doesn't have its normal number of bonds, it's got a formal charge of something other than 0. But let's check here for this oxygen. In fact, for all 6 of the singly bonded oxygens. 6 valence electrons minus 1 bond to the atom plus 6 lone pair electrons. 6 minus 7 minus 1. That means this atom has a formal charge of minus 1. So does this one, and 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 you add up the 2 minuses and you get the 2 minus that you see overall. But that's not the overall goal here, although now you guys know how to write out Lewis structures for ions. The question now becomes, well, I have 3 Lewis structures here. All of these are valid according to the Lewis structure rules. Which one is the most valid? Well, neither of them is most valid, and all of them are most valid at the same time. They're all equally valid. And what that means, these actually exist kind of in flux with each other. These are what are called resonance structures. And what that means is they differ only in the location of 1 pair of electrons in a pi bond, this double bond here. And so the actual structure of the CO32- is somewhere in between each of these 3, where 30% of the time the double bond's here, 30% of the time the double bond's here, 30% of the time the double bond is here. So if you were to analyze this ion and you were to observe the length of each of these bonds, you would not see 2 single bonds and 1 double bond. What you would see would be 3 bonds that are all the same length, which have a bond length between a single and a double bond. Because the actual structure, the so-called resonance hybrid, lies between each of those 3. And in fact, the structure of the hybrid would look something like this. It's going to look kind of funky, but I'm going to do it anyway. Because the double bond is sometimes here, I'm going to put a dotted line there, dotted line here, dotted line here. And because the negative charges are not on any particular atom at any point, the 2- charge extends throughout the whole molecule. Those are resonance structures, and you can see we figured those out from using the concept of formal charge. Now there is one other thing I do want to look at though as far as formal charge goes. You have some cases where, let's say we have a molecule like this, an ion like this, OCN minus. And we have to ask ourselves, can you give me all the possible resonance structures? And it turns out there are 3 here. All the possible, not resonance structures, all the possible structures for this. And I want you to tell me, based on formal charge, which one is most valid. All right. Now these are all resonance structures with respect to each other, but unlike here, where they're all exactly the same and thus equally stable, the ones that we're going to draw here are different. All right. Now, OCN minus, oxygen's got 6 valence electrons, carbon's got 4 valence electrons, nitrogen has got 5 valence electrons. We're adding 1 electron to it because it's OCN minus. 9, 15, 16 valence electrons to place. All right. Now we know for a fact that we're going to put at least single bonds between all these, so let's put these here. But look at the carbon first. The carbon we've always seen has to have 4 bonds to it, and thus have 8 electrons. And it turns out there's only 3 different ways to draw 4 bonds to this carbon. One way is by doing this. You know what, let me do that again, that looks like crap. One way is by doing this. One way is to put a triple bond here and a single bond here. The other way is to put a single bond here and a triple bond here. But now we've got to finish off our octets. So carbon in each case has its 8 electrons. So we're going to put lone pairs on the oxygen and nitrogen in each case, depending on what we need to do. Oxygen here, 4 electrons, so therefore it needs 4 more. Nitrogen, 4 electrons, therefore it needs 4 more. Oxygen here, 6 electrons, therefore it needs 2 more. Nitrogen here, 2 electrons, therefore it needs 6 more. Oxygen here, 1 bond, 2 electrons, therefore it needs 6 more. Nitrogen, 6 electrons, therefore it needs 2 more. 16 valence electrons, so 2, 4, 6, 8, 10, 12, 14, 16. 2, 4, 6, 8, 10, 12, 14, 16. 2, 4, 6, 8, 10, 12, 14, 16. So, according to Lewis structure theory, each of these are valid. And they are all valid, but some of them are better than others. Some are more valid because they're more stable than others. And that is where formal charge comes into play. So we're going to figure out formal charge of each of these guys. Let's start off with the oxygen. Note, though, we're not going to worry about it for the carbon because each of the carbons has 4 bonds. So those are fine. Let's look at this oxygen here. 6 valence electrons minus 2 bonds to the oxygen plus 4 lone pair electrons. Formal charge of 0. Notice that's the only oxygen with 2 bonds to it. So what that tells us here, 3 bonds and 1 bond, both of these oxygens are going to have formal charges other than 0. Therefore, this looks like the happiest situation for oxygen. Anyway, let's look at this oxygen here. 6 valence electrons minus 3 bonds to the oxygen plus 2 lone pair electrons, giving us 1. We have a formal charge of plus 1 on the oxygen. You don't need to put your charges in circles, I just got used to doing it that way, so that's what I do. Plus I think it looks cute. Now this oxygen over here. This oxygen has 6 valence electrons minus 1 bond to the oxygen plus 6 lone pair electrons, giving us a total of minus 1. As far as we're concerned right now, minus 1 nor plus 1. If we just look at the formal charge, neither of these would tell us which is less stable, because the magnitude is 1 in each case. But there's one other thing we're going to look at here in just a minute to differentiate these. But let's look at the nitrogens though. Nitrogen here. Nitrogen's got 5 valence electrons minus 2 bonds to nitrogen plus 4 valence plus 4 lone pair electrons, giving us a total of minus 1. So there's a minus on the nitrogen there. Let's move over to this one. Nitrogen again is 5 valence electrons minus 1 bond to the nitrogen plus 6 lone pair electrons, giving us a total of, oh dear, -2. Oh, that's not good. That's not good at all. You remember we said before, -2. That's not good. Now when we come over to this one, nitrogen, 5 valence electrons again, minus 3 bonds to the nitrogen, plus 2 lone pair electrons, giving us 0. Alright. Now we are all set to figure out which of these structures is the most likely resonance contributor. Alright. And the overall goal is we're looking for the one that has the least, the formal charges that are the least spread out over the molecule. So we're looking for formal charges. Basically, we're looking for the least number of formal charges possible. If we have a situation where we've got formal charges 0, no formal charge, 1, -1 here, 0, 1, -1 here, and then we have formal charge of other than 0 on both these atoms, that says this one is less likely, plus the fact we have a -2 says that's even less likely. So we can rule this one out as being the most likely resonance contributor. So then we've got to figure out which one of these two is it. And this is where it gets to be quite close, because notice the formal charges are 0 and -1 in each case. So you can see, just looking at the formal charges themselves, there's no differentiation that we can make, so it looks like we're kind of stuck. But we do have one ace up our hole. Oh my god, that sounds horrible. We don't have an ace up our hole. Oh dude, we have an ace up our sleeve. We have other things up our... Oh no, never mind. Oh dear. Okay. The formal charges here are both 0 and -1. So we've got to have one other way to differentiate them. And that is very simply, the -1 implies, well, I've got more electrons than I want here. So the most stable resonance contributor is where the most electrons, or where the more excess of electrons is on the more electronegative element, because electronegative elements pull electrons towards themselves more than others. So the question comes down to then, which element between nitrogen and oxygen is more electronegative? You've seen before, oxygen is more electronegative than nitrogen, is closer to fluorine. Because of that, although it's a close call, this Lewis structure for OCN- is the most stable resonance contributor, is the biggest resonance contributor. Then this one, and this one is a this one's a close second. This is not a close third. And so that's how you use formal charge to figure out stability of resonance contributors. All right, and we talked a little bit about resonance and what it means, and we've just seen how useful formal charge can be. All right, thank you.